Sports. That's a crazy intro. Last class we left off, we were talking about ions. And specifically we talked about our fourth intermolecular force, the ion dipole force. Take a short moment and think, what are the other three forces? Where do they show up? Great, now that we've thought through all of that together, individually. Ion dipole force was our last force. That's the force between, you guessed it, an ion, like sodium or chloride, and a dipole, like on polar molecules, which have dipole-dipole forces. That's our second force. Ions can also conduct electricity. So pure water, you may know, probably didn't, does not conduct electricity at all, like basically at all. You can get it to conduct electricity, but it's super, super resistive. So you've maybe heard the age-old wisdom that the projector is bumping up and down to the beat. The age-old wisdom that you shouldn't make toast. You shouldn't bring your toaster into the bathtub with you, because if the toaster falls in the bathtub, you'll die. Maybe you are aware of that. You shouldn't do that because you'll die. However, if we had pure water, absolutely pure water, it would be safe to make toast in the bathtub because it wouldn't conduct electricity, and so if the toaster fell in, it would just be wet. And that's kind of all that would happen. But our bath water is not pure water. So that's a fun fact for you. And part of why it's not pure water is because there's ions in there. Ions, things like sodium chloride, anything that produces positively and negatively charged particles, can conduct electricity. And so if you put a negative lead and a positive lead in some salty water, you can get a light bulb to light up. You shouldn't do this at home because it's super dangerous. So we're just showing you this rendering of it. And that's why bathing with a toaster is bad. So pre-make your toast and then bring it into the bathtub with you instead of making it while you're in the bath. That's the takeaway here. You can also get solutions that have low conductivity, things that are not strong electrolytes. So KCl, potassium chloride, sodium chloride, other chlorides, are called strong electrolyte solutions. The strong meaning that they dissociate completely. Crazy letter to start with. So strong meaning that they completely dissociate or separate. And the electrolyte part meaning that they conduct electricity because they're ions. Gatorade notably is full of electrolytes. Same type of electrolytes that you drink to replenish when you sweat a lot. So electrolyte solutions generally contain dissolved ions and they conduct electricity. There are also non-electrolyte solutions. Since they're not electrolytes, they don't conduct electricity. They don't contain dissolved ions. They contain dissolved molecules. What are molecules made of? Nonmetals. And only nonmetals. No metals in my molecules. So non-electrolyte solutions contain dissolved molecules instead of ions. These are neutral particles, and they don't conduct electricity. So things like sugar water. Sugar is a molecule. And because it's a molecule, it's not a charged particle, and so it won't conduct electricity because it doesn't have a positive or negative charge. It doesn't move with the electric flow. A silver nitrate solution, AgNO3, as it turns out, does not contain any silver nitrate units. So if we take this really cool beaker and we put some silver and we put some nitrates in there, we put like silver nitrate solid in there, it completely dissolves. We're going to find silver ions surrounded by water molecules. We'll find nitrate anions surrounded by water molecules. No AgNO3 units. And this means that it's a strong electrolyte solution. It's completely dissociated. Every single little bit got torn apart, ripped to pieces. Another thing to talk about here is that when compounds containing polyatomic ions dissolve, the polyatomic ions dissolve as intact units, unless there's a chemical reaction that happens. Generally, if we're just dissolving stuff, though, there's not a chemical reaction happening. So our nitrate units stay intact as NO3-. If you put AgCl in water, we've actually got some of the water rendered in here. If we put AgCl in, it remains a solid AgCl. It's still got silver, but we've swapped out the nitrate for chloride, and now it doesn't dissolve. Why? Beyond the scope of this class. But we can say with confidence that it does not dissolve. Or at least it does not dissolve very much. It's a negligible amount, an ignorable amount. So despite all these water molecules' best attempts, best intentions, worst intentions, they cannot rip apart the AgCl solid that we've added into our water. When you mix together things, you can make an aqueous solution. Have we talked about solutions? I feel like we have, but I'm also teaching Chem 1, and so I feel like I'm going crazy, and I can never remember what we talked about. Okay, great. I'm pretty sure that we did. So a solution, just as a reminder, is a homogeneous mixture. That means we're well and evenly distributed throughout. Think like Pepsi. If you drink from one part of a Pepsi and the other part of a Pepsi, not that there's only two parts, but if you drink from two different parts, should taste the same, versus if you leave water and oil and you just let them separate out. If you drink from the water part, it's going to taste like water. If you drink from the oil part, that's really gross. Don't drink from the oil part, because it's just oil, because they separate. It's not homogeneous, it's a heterogeneous mixture. So homogeneous mixture, these are aqueous solutions, the aqueous part referring to water. So I'll tie those together. Look, tied, connected. So when ionic compounds dissolve in water, they usually dissociate into their component ions. So whatever ions went into making that compound, those are the ones that get separated out. For example, with sodium chloride, you can stir table salt, because that's usually sodium chloride, into a glass of water. And it visually looks like the salt has disappeared. It has not disappeared. It's just not in big chunks anymore. It's broken down into little ion bits. And you know that they're there because the water tastes salty. These compounds, things like table salt in water, are soluble because they dissolve. Soluble, it dissolves. If things do not dissolve, then we call them insoluble. We're using this in prefix to mean not. I skipped the O. Does not dissolve. So things that are insoluble, do not dissolve, does not dissolve in that liquid. So that would be like the AgCl that we saw, where we added it into the water and it stayed completely intact. It didn't get separated out into its component ions. For ionic compounds, what kind of things are in ionic compounds? Metals and nonmetals. So things that have metals and nonmetals, things that have ions, just generally, positive and negatively charged ions. We have some empirical rules of solubility. These are based on a lot of different observations of many different compounds. So a bunch of people took a bunch of different chemicals and said they put it in water and it does dissolve. Okay, write that down. Different compound. It does not dissolve. Okay, write that down. Different compound. It does dissolve. Okay, write that down. That's all that empirical means. So just based on observations of actually trying to dissolve stuff, we've got these rules. And these are summarized in these tables. You also have it on your green sheet on the side that says solubility table at the top. So we are finally getting around to using this side of the green sheet. Solubility like many other things in chemistry, contain many exceptions. So there's lots and lots of exceptions. It's important that you be able to read a solubility table and understand what you're looking at and whether the compound that you're trying to find is soluble or not soluble. You will be provided a solubility table on exams. I don't expect you to have it memorized. Some of them you might memorize eventually, just like through using them, but I would say generally you don't have to worry about memorizing solubility rules. This is a solubility rules table from our online book. It's slightly different from the one that's on our green sheet. So the way that these solubility rules work is we've got a soluble part up top, same as our green sheet. And so things that are up in this group, in this soluble in water category, or in R's group or ion, it's going to say a bunch of things. So anything that's in group 1A, so if we look at our periodic table, the far left column or group, lithium, sodium, potassium, rubidium, cesium, francium, all of those things, and ammonium salts. Salts is just referring to ionic compounds, like table salt, which is a specific salt called table salt. So all of those things are going to be soluble in water, unless it's one of these exceptions. For these, no exceptions. It's always going to be soluble. If we look at something like sulfates, sulfates are also going to be soluble. Sulfates, of course, being anything that has SO4 2- in it. Those are always going to be soluble, except if we look over here, calcium sulfate, barium sulfate, strontium sulfate, lead 2 sulfate, those are not going to be soluble. So if you have one of those exceptions, those are not soluble. So this left side, things that are soluble. This right side, things that are not soluble. Let me move this so you can still use it. Not so lubable. Not soluble. And then we've got another set of table down here. And this is things that in the online book it says sparingly soluble. You can basically interpret that as not soluble. It's not going to completely dissolve. Everything kind of dissolves to a small extent. Generally speaking, though, it's not dissolved. So all carbonates, all phosphates, all hydroxides, all sulfides, all oxalates. So oxalates being C2O4 2- things. Like it might have sodium in front. Like sodium oxalate, Na2C2O4. And generally speaking, these are not going to be soluble because it's got the C2O4 2-. However, we have an exception, and since we have an exception, we've got a group 1A in here, we've got sodium. Since we have that exception, this Na2C2O4 is soluble because it meets the exception. Do you have any questions about how to read the table? So you're going to, if you're given a compound, you go and look, where do I find the positive charged ion or negative charged ion or both? Where do they show up in here? And then see if there's any exceptions for the specific compound that you're looking at. That's all there is to it. Okay, so solubility rules give us a qualitative description of the solubility of ionic compounds. There are no numbers involved in qualitative descriptions. We're describing qualities like big, strong, muscular, weak, little, baby-faced, other things like that, qualities of the solubility of ionic solids. Obviously, none of those descriptors match for solubility. So we're just saying it's soluble, it's not soluble. You might sometimes say it's kind of medium soluble, but we're not putting any fine numbers to it. Some ionic compounds, like calcium carbonate, are insoluble because the attraction between the ions is greater than the solvent-solute attraction, which we had looked at last class. And let me see if I can find, here it is. So the solute-solute attraction, the attraction between the ions, is stronger than the water and the ions. So the solute says, no, we're fine, we don't want any water here. Please go on to the next ionic compound. and the water very respectfully does so. Okay, molecular solids can also be soluble in water depending on whether the solid is polar. Water is polar, and we have this saying, like dissolves like. So things that are polar will dissolve in things that are polar. So things that are polar like table sugar, C12H22O11, is polar and it will dissolve in water. Things that are nonpolar solids like lard and vegetable shortening are typically insoluble in water. They're just going to sit there. Okay, let's determine whether some compounds are soluble. So even if you don't have your green sheet, we've got up here on the screen some solubility rules. Please determine whether each of these compounds is soluble. Feel free to discuss with your neighbor. All right. Let's see if each of these compounds is soluble or insoluble. First one up, we have calcium sulfide. Calcium sulfide. So this is a type of sulfide. So we're going to look for either calcium or sulfides. In this far left column, we find it down here, all sulfides. All sulfides are sparingly soluble, which basically meaning that they're not soluble, or at least not completely soluble in water. And if we look for an exception, because we always have to look for an exception, we can see that there is one for calcium sulfide, and so calcium sulfide is going to be sparingly soluble. So we will write that in as soluble. And on our green sheet, it's the same thing, it just doesn't say sparingly soluble. And then we've got FeSO4, which is going to be iron 2 sulfate, or ferrous sulfate. So we're going to find iron 2 or sulfate. I should have done this in a different color. We find sulfates here in our soluble in water. And let's see if there's any exceptions for iron. It looks like we don't have exceptions for iron 2, so that means that this is soluble. The other one was soluble because it's insoluble, but exception. Okay, and third up we've got PbCO3. Pb is lead. This is going to be lead 2 because carbonate has a 2 negative charge, CO3 2 minus. Or we could also call it plumbous carbonate. So we're going to look for anything that has lead 2 or carbonate in it. We can find carbonates in the sparingly soluble category. This is not soluble because we don't have an exception here for lead. We've got group 1A and ammonium salts as our only exceptions here. We don't have that. We've got lead 2. And then we've got, as our last one here, ammonium chloride. So we're going to be looking for ammonium or chloride. We've got ammonium up here, and we've also got chlorides. So this shows up in 2 different spots, but just based on this first one, it's soluble in water. There are no exceptions for ammonium salts. So this is soluble, because we don't have an exception. Questions about any of those, how we got them, how we read them from the table? I think historically I've gone easy mode and given you the green sheet solubility table. Although I guess I could make it hard mode by just giving you like the name instead of the formula. I don't remember which I do. You should know your nomenclature, so it's not a problem. All right, why are we learning about solubility? It's not just because, but it's partly just because. The big reason that we're learning solubility is so that we can talk about precipitation reactions. If you look at the weather forecast, and there's rain, there's snow, there's sleet, there's hail, there's a lightning storm, what can we describe all of those different weather events as? Precipitation. Outside the bounds of this class, but hopefully you knew that precipitation is a word for things that fall from the sky, just kind of generally. Where did it come from? Does somebody have a big hose up in the sky that they're just like spraying water down on us? Some people might think so, but that's not the case. It's just appearing out of nowhere. Precipitation reactions have a similar vibe. It's just suddenly we have a solid, suddenly something appeared. So as an example of where precipitation reactions play out, sodium carbonate is commonly used in laundry detergent. This is very important, particularly for where we live since we have hard water. So this sodium carbonate can react with dissolved magnesium and calcium ions that are in our water, and these form solids that precipitate out of solution. Calcium and magnesium ions interrupt the action of detergents or soaps, like your shampoo, your body soap, whatever other soaps you might use. It interferes with their action to remove dirt and grime, and especially in your laundry where presumably you're washing dirty clothes. It's important that you get a good lather. You can't just kind of like go into your laundry machine and like add more as you're going. Maybe you can if you've got a top loader, but generally not something that you're probably going to want to do or necessarily even be able to do. So adding sodium carbonate to laundry detergents helps take those ions out of the picture, and it lets your laundry detergent do the work it's supposed to. These reactions are examples of precipitation reactions. Precipitation reactions are described as reactions that form a solid upon mixing two aqueous solutions. And I'm just going to box the whole thing in because it's all important. Okay, so the big takeaway, what is a precipitation reaction? It's a solid that forms from mixing two aqueous solutions. So if you have two solutions, homogeneous mixtures where everything's dissolved, and you mix them together, and then poof, suddenly out of nowhere, a solid. That's a precipitation reaction. That poof out of nowhere part, that's how it connects with what we call the precipitation, like related to weather. And the precipitate is the solid. That's what we call that. So an example of a precipitation reaction, if you take potassium iodide, Ki, and you mix that with a solution of lead 2 nitrate, PbNO3, 2, a brilliant yellow precipitate of PbI2 lead 2 iodide forms. That looks something like this. So we've already mixed the two aqueous solutions together, and boom, magically, yellow solid appears. However, precipitation reactions don't always occur when mixing two aqueous solutions, so it's entirely possible that you mix two things together and all that happens is they mix. Happens. The key to predicting, we get to predict. The key to predicting precipitation reactions is understanding only insoluble compounds form precipitates. So if no solid is formed, no reaction occurs. No precipitation reaction occurs, at least. So in a precipitation reactions, two solutions containing soluble compounds combine and an insoluble compound comes out as a solid. That's what we're looking for a precipitation reaction. If you don't form a solid, it's not a precipitation reaction. There's other reactions that could happen, but it's not a precipitation reaction. All right, so let's look at some examples, or an example. This is what we were looking at previously. So we've got Ki and PbNO3 They're both aqueous. The AQ at the end, remember, means that they're dissolved in water. So we know for sure that the ions have separated out into their positive ions and negative ions. So in solution, excluding showing all the water molecules, we've got potassium, we've got iodide, we've got lead 2, and we've got nitrate dissolved. And I'm just showing a limited number of each of the ions here. That's before mixing. They're dissolved, they're completely separated, completely dissociated, strong electrolytes, all that good stuff. Immediately after mixing, before they've had a chance to react, this is what our flask would look like. What possible combinations of ions do we have? Can somebody give me a possible combination of ions? What are two ions that can go together? How do ions combine? Bueller? Bueller? Anyone? Somebody name an ion. Potassium. We have a potassium ion. What kind of charge does potassium have? Potassium has a positive charge. Positive charges attract what? Negative charges. Can somebody name a negatively charged ion that we have? Nitrate. Okay, so those could possibly go together. So that would be KNO3. Is there another ion that potassium could go with? Potassium could also go with the iodide. Do we have another positively charged ion? We've got lead, Pb2+, and this can also get paired up with the nitrate, which after we crisscross would be PbNO3 2. It could also be paired up with the iodide, which would give us PbI2. So if a precipitation reaction is going to occur, these are the four possible products. These are the four things that we could possibly look up in our solubility table and see, are any of these going to be solids? However, we already know that two of these are soluble. How do we know that two of those are soluble? Because they were previously dissolved, right? So we don't have to recheck Ki. We don't have to recheck PbNO3 So the only two that we would have to look at is if we swap some of the ions, the new pairings. So these two were already aqueous or dissolved. So we don't have to look those up again. We just look at the new ones on our solubility table. So we would be checking for KNO3 and PbI2, the new combination of ions. And if we do that, we would find that PbI2 precipitates and potassium and nitrate ions remain in solution. If you look at your solubility table, the third line on the soluble has iodine or iodide, and there's an exception for lead 2+. That's how we would know that this precipitates. Questions about that process? Conceptual parts of the process. Positively charged ions pair with negatively charged ions to form neutral compounds, formula units. We can check those to see if there's something that's not soluble. Here's those steps written out on one slide. So to start, writing an equation for a precipitation reaction. We want to write the formulas of the two compounds being mixed as reactants. Which side do the reactants go on, left or right? Left. Reactants are on the left. So we're going to write them in on the left of our chemical equation. And then we'll put an arrow, because presumably these are going to go on to form something new, or could form something new. And then below that equation, below our two compounds being mixed, below our two reactants, we're going to write the formulas of the ions. So we're going to separate into ions. We have to remember to include the charges. So we'll split the positive and negatively charged ions from our first reactant, the positive and negatively charged ions from our second reactant, and then we are going to exchange anions. Anions are negatively charged. So we'll swap the negatively charged ions. That ensures that we get new pairings. We'll show the steps soon. And then we'll rewrite the ion formulas below the product side, and then we'll combine them up and see if any of those new pairs is insoluble. If both pairs are soluble, then we just write no reaction or choose the no reaction option. Nothing happened, we just mixed them together. That's not a chemical reaction. If one or both of the new ion pairs is insoluble, that means that it forms a solid. Then we'll write the formulas of the compounds after the arrow as the products. We'll use AQ to indicate which one is soluble, which one stays dissolved, and use the S to indicate the insoluble product, our precipitate, which is a solid. Then we can balance the equation, because we still have to balance the equation, by adding coefficients. And remember that we're not changing subscripts. So we're only changing the number in front. We're not changing the number behind. So for example, if we have this, the 2 in front as a coefficient, the 2 behind is the subscript. The sub meaning that it's lowered instead of being raised or in the line of the text. If you've forgotten how to balance equations, Logan knows how to balance equations and would love to show you instead of doing whatever other homework he has. So please go to his SI session so that he doesn't have to do his homework yet. Okay, let's predict. Let's look into the future and see if we mix aqueous solutions of rubidium hydroxide and cobalt 2 chloride, what happens? So we need, what's rubidium, what's hydroxide? If we're starting with names, we're going to have to come up with the formulas. So you might want to just start with writing down the ions below. So rubidium is Rb+, hydroxide is OH-, and those are going to have a 1-to-1 ratio when you put them together, so it's RbOH, because they're both a 1 charge. We put the AQ behind it to let us know that it's aqueous, it's dissolved. We already know that it's soluble. Our other reactant is cobalt 2 chloride. What does this 2 mean? Think to yourself for a moment. What does that 2 mean? Why did we include a 2 there? We didn't include a number for rubidium hydroxide. Why did we put a 2 for cobalt? We put a 2 there because it has a 2 positive charge. The 2 refers to the charge of the cobalt, not to the number of cobalts that we have. This is a common error that I see. That's the charge, not the number of cobalts that we have. So we've got CO, little o, C little o, 2 plus. We've got chloride. Chloride is one of our halogens. It shows up in group 17 or 7A, Cl, which means that it has a 1 minus charge because it's one spot over from our noble gases. It needs to pick up 1 electron to get to the noble gas configuration. And when these combine, because cobalt's a 2 plus and Cl's a 1 minus, we're going to have 2 chlorides. So this is CoCl2. Logan would also love to help you with nomenclature. And we also know that this one is aqueous. All right. Now, we need to see what our potential products are. And the way that we can see what our new pairings are is if we swap the anions, the negatively charged ions. You could swap the cations instead. I just swap the anions. It doesn't matter as long as you only swap one pair, don't swap both, because then they just have switched locations and that doesn't mean anything. So we're going to swap the hydroxide and the chloride. And we're going to rewrite this on the right side. So we've still got our Rb plus. Now it's paired with the chloride. So Rb plus, Cl minus, and then our other pair is our CO2 plus, and the CO2 plus is now paired with the hydroxide, the OH minus. And then we have to combine these to figure out what our products are. You could also, if you don't want to do the little swap and drop and put the products in, you could just go ahead and take a look at your solubility table now to see if either of these is soluble. And let's go ahead and do that. So we're looking for rubidium or chloride. On our green sheet, if we look at the third line in the soluble part, we've got Cl minus. Cl minus is generally soluble. Do we have an exception for rubidium? We do not have an exception. So this compound is soluble. We would do the same thing for our CO2 plus and our OH minus. We find OH minus on the very last line of our insoluble. So hydroxide is generally insoluble or not soluble. Do we have an exception for cobalt 2 plus? We do not have an exception for cobalt 2 plus. Since we don't have an exception, that means that it is insoluble. Okay, so now we can recombine these. Rb plus and Cl minus are 1 plus and 1 minus, so those charges will balance each other out, so we can just combine them 1 to 1. RbCl. We determined that this is soluble, so it's AQ. And then our other one, CO2 plus, OH 1 minus, we're going to do our crisscross or swap and drop. And this will be CO, OH, and then a little 2 down there. It's important that we remember the parentheses. If you don't include the parentheses, then it would look like we've got just 2 hydrogens, which would then just make it cobalt water, which is not a thing, as far as I know. But maybe it'll be in a grocery store soon. And this one, what do we give the symbol behind it? S for solid. So this is S. Are we done? We're not done. What do we have to do left? We have to balance it. So for balancing, for precipitation reactions are a class of double displacement or double replacement reaction. So they follow, there's my favorite way to balance them. I don't know, I'm being a diva up here. My favorite way to balance them is let's look for something that's different on both sides. What's a cation or anion that's different on both sides? We don't have the same number on each side. Chloride is an option. Hydroxide is an option. Let's do chloride because it shows up on the left first with the 2. It's mismatched on the left. So we've got 2 on the left because of this subscript of 2. So 2 chlorides. On the right, we've got 1 chloride. That's not enough. Got to get those numbers up. So we're going to put a coefficient of 2 in front of our RBCl. Coefficient, not subscript. And that gets our number up to 2. When we did that, what changes? Other than the chloride, what changes? The rubidium. The Rb also changes, and so we are going to balance that next. So the Rb, we just figured out there's 2 on the right side, because we just adjusted that. On the left side, how many do we have? We have 1 on the left side. 1 is not equal to 2. So we're going to need a 2 in front of our RbOH. That'll bump up our rubidium to 2. When we did this to adjust rubidium, what's the other thing that we changed? Hydroxide, our OH, and so we're going to balance that next. So for our OH, we just changed it on the left so that we've got 2. If we look on the right, look at that, we've got 2. Usually when you get to this point, that means that you're done, but just for due diligence, let's check our last thing, which is cobalt. So our cobalt, we've got 1 on the right, 1 on the left, perfectly balanced, as all chemical equations should be. Questions? All right. Let's skip to the one that you do. Here's one for you to do. Since there were no questions, I assume that we're all experts, or we're shy. Either way, take some time, try to figure it out. And after a short amount of time, I might just give you the formulas in case we're stuck on the nomenclature. All right, if you were stuck on the nomenclature, we've got aqueous solutions of potassium sulfate. Potassium is K. So it's going to be K2SO4. It's aqueous. So we put the AQ after it. And then we also have lead 2 nitrate, PbNO3 2. All right. So we've done our first step. We've got our reactants, our 2 aqueous solutions, and I forgot the AQ after this other one. So we've got 2 things that are dissolved. We need to separate these out into the K plus, the SO4 minus, the Pb2 plus, the NO3 minus. We are then going to swap our anions and rewrite them under the product side. So our K plus stays in its spot. It's going to be paired up now with NO3 minus because we moved that. And our Pb2 plus, our lead 2, is going to be paired up now with sulfate, SO4 minus. And we can recombine these. Conveniently, there are 1 plus, 1 minus, 2 plus, 2 minus. So it's just KNO3 and PbSO4. And then we have to find on our solubility table, are these things soluble? So we look for potassium and nitrate. If we find potassium, potassium's on the soluble table. It's in the very top bit, group 1. And there's no exceptions. So this is soluble. We'll just write an AQ after that. So this one's soluble. Let's see if we have a reaction with lead 2 sulfate. So we find sulfates. Sulfates on our green sheet is the last row of the top section of the table. So that's the generally soluble. Sulfates, generally soluble. And we have to check for exceptions. And so if we look over to the right, except for those containing Ca2+, Sr2+, Ba2+, Ag+, and look at that, Pb2+. So we do have an exception. And an exception means that it's insoluble. So insoluble, meaning that it's a solid. Questions about that part, because that's the new stuff. All right, and then we have to balance it. And to balance it, we just put a 2 in front of the KNO3. So that's cool. And now it's balanced. Magic. All right, I know that you're all wondering, wanting more. Turns out there is more. So we've primarily been looking at molecular equations. This is the type of equation, chemical reaction equation, that we've been looking at exclusively. Molecular equations show the complete neutral formulas. Complete neutral formulas for every compound in the reaction. We could also call it a complete chemical equation. We have other types of equations, as implied by us talking about one type of equation. That other type, first other type, is complete ionic equation. So complete meaning everything, the whole kit and caboodle, and ionic meaning ions. So the complete ionic equation is going to show all of the ions, complete ions. So we're going to show aqueous ionic compounds as ions. So our AQ compounds get separated into ions. The positive and the negatively charged ions. We are not going to be separating solids, liquids, or gases because they are not dissolved. The reason that we're separating these AQ compounds is because in actuality they are dissolved, meaning that the positive and the negative are separated in solution. So our complete ionic equation is showing us what does it actually look like in solution without us having to draw stuff, because this is not an art class. So molecular equation, everything combined, really nice and succinct. Our complete ionic equation, we're going to separate everything that's AQ. And when we do that, we will find that we have some spectator ions. What do spectators do? They watch, they spectate. They don't participate in the game, right? If you buy a ticket to an NFL game, you are not going to randomly and suddenly get called down by one of the coaches like, hey, we need a kicker, you're our guy now, right? You're just going to be standing there, you're sitting there watching. You might get some free swag thrown at you, or a beer poured on you, depending on what sort of situation you find yourself in. So spectator ions, just like spectators at football games and other games, are ions that are unchanged on both sides of the equation. They just watch. They do not participate. So these are unchanged on both sides of the equation. So if it shows up on the left side, the reactant side, if it shows up on the right side, the product side, and it's the same, we're doing a comparison, find the differences. If it's the same, we can get rid of it. And when we get rid of it, that gives us our net ionic equation. A net ionic equation shows only the stuff that participates. Remove the spectators. And species in this context means just any sort of thing. We're talking about molecules or ions in this case. Chemical species. I was thinking of a thing. Net. If you work and you get a paycheck, you've maybe seen your paycheck. You're like, this is how much they're paying me. Awesome. I love that. And then you get your first paycheck and you're like, that is not the number. Where are the rest of the numbers? Because what you get paid is the net pay. You get net pay. There's gross pay. Gross pay is like our complete pay. And then if you take all the taxes and fees and whatever else out, right, what you get left over after all the other stuff is taken, that's your net pay. Our net ionic equation is just what's actually doing work. And here's a summary of our equation types. So our molecular equation shows complete neutral formulas. Our complete ionic equation shows everything as they are in solution. Ions are separated if it's AQ, if it's dissolved. And then our net ionic equation, we're taking out all the taxes. We're removing the spectators. Okay. Consider this reaction occurring in aqueous solution. We've already shown you, well, here's our reactants, here's our products. Please write the complete ionic equation and a net ionic equation for this reaction. Before we do that, is this equation balanced? Any guessers? It is balanced, and we can guess that because we've got a coefficient in there. Usually if there's coefficients given to you with a problem, it's usually balanced, always safe to check, but because we've got this 2 in front of NaCl, yeah, it's probably balanced. So go ahead and write out that complete ionic equation and also the net ionic equation. All right, coming up with our complete ionic equation, we are going to be separating things into their ions. What things are we separating into their ions? How can we tell what we're separating? Anything that's got AQ after it means that it's aqueous, means that it's dissolved in solution. We're trying to reflect how it actually looks into solution. So our complete ionic equation, we are going to separate all of these things with the AQ tag after them. So for our BaCl2, we're going to have Ba2 plus 2 Cl minus. There's 2 separate chlorides for every BaCl2. We could also optionally include AQ after every single one of these ions. I think it goes without saying that they're dissolved. I also don't want to write AQ 8 times, 6 times. So we're not going to do that. And then we've got, for our Na2SO4, our sodium sulfate, we've got 2 Na plus SO4 with a 2 negative charge. Then we get to barium sulfate. Barium sulfate is a solid, so we're just going to rewrite it. BaSO4, I'll put the S after it. And then we also have 2 Na plus and also 2 Cl minus. This is our complete ionic equation. Now we want to pare this down, P-A-R-E, this down. to our net ionic equation. What are we removing when we go to our net ionic equation? Small potatoes. Yeah, we're removing the spectators. So our net ionic equation, we're removing the spectators. How can we tell what things are spectators? They don't change. They're the same on the left and on the right. There's a couple of fast ways to tell. BaSO4 here is a solid, so anything that went into that obviously participated in the reaction. So we can say, all right, we're going to lock in barium and sulfate. That's one way that we could figure it out. The other way, we've got sodium and chloride both dissolved here at the end. They didn't produce a reaction, so they're also going to show up as the same on the other side. Either way, we are removing our sodium and our chloride. So all that's left is Ba2 plus, SO4 2 minus, and those combined to form BaSO4 as a solid, barium sulfate. Questions about complete ionic equations, molecular equations, or net ionic equations? Or questions about solubility? Okay, that wraps up Chapter 9.